Hello everyone, my name is Anisha Singh and I'm going to present my paper which is detecting missing permission check vulnerabilities in distributed cloud system. So let's understand first what is missing permission check vulnerabilities or MPCs. They refer to a type of security issue where permission checks are not properly enforced for privileged operation within a software system. In distributed systems, MPC vulnerabilities can arise when critical operations that require specific permission or privileges to execute safely are not adequately protected by corresponding permission checks. These vulnerabilities can lead to unauthorized access, data corruption, leakage of sensitive information. In the abstract, the author advocates for the efficacy of a new tool called MPC Checker, which, as its name suggests, is a tool that is used to check for MPC vulnerabilities. The author states that they have tested this tool across 6 systems and were able to identify 44 vulnerabilities. So let's take an example to understand more about MPC vulnerabilities. The vulnerabilities depicted through a privileged operation, specifically the invocation of method data.delete block pool, which requires certain permissions to execute safely. However, in the code snippet, there's a lack of corresponding permission check to guard this privileged operation, leaving it exposed to potential misuse or unauthorized access. To address this vulnerability, a permission check function checks super user privilege is introduced at line 2 in the code snippet to validate the necessary permissions before allowing the execution of the privileged operation at line 7. In addition, a permission check serves as a protective measure to ensure that only authorized users with the required privileges can access and execute the critical operations, thereby mitigating the MPC vulnerability. So there have been a lot of existing efforts to combat missing permission check vulnerabilities, which involve manual specification of permission check in operating systems and web applications. These approaches typically require specifying permission checks in a centralized module, making the manual effort manageable. Once permission checks are identified, privileged operations are mined based on the assumption that they are typically guarded by permission checks on most program paths. Inter-class procedural data flow analysis is then applied to identify vulnerable program paths with unguarded privileged operations. While these approaches work well for privileged functions that are partially protected, they may not be directly applicable to distributed systems due to the challenges posed by the separation of permission checks and privileged operations across different components. There have been a lot of challenges in distributed systems. Existing approaches designed for specific system may not be directly applicable to distributed system because of different components involved, and they are implementing a lot of different or distinct permission checking mechanism, which makes it difficult to examine and specify all permission checking mechanism. Also, around 32.6% of permission checks are done ad hocly by testing user variables and conditional statements. So specifying these conditional statements is a hurdle. Analyzing MPC vulnerabilities in distributed system poses a unique challenge, such as understanding the intercomponent interaction. Since it's a distributed system, there are more than one component involved. So understanding those interactions is the main point. Other than that, incomplete call graphs due to communication mechanisms like RPC and the scalability of static analysis across multiple components also poses a challenge. Let's talk about a few solutions that were proposed by the authors. The author approach aims to automatically identify permission checks and privilege operations in distributed systems by inferring variables representing in user-owned data and critical system states. User-owned data being data meant only to be seen by the user, and critical system states being states that can only be written by super users. The issue is identifying user-related variables and system-related variables automatically. Their study indicates that most user-related variables, actually around 90%, are printed in log statements. So hence they can apply the log analysis together with static analysis to infer user-related variable. Specifically, given the set of all the username, they can check runtime logs to discover variables printing the same name as the user. A type-based static analysis is followed to discover more user-representing variables in the program. Variables representing user-owned data are discovered via correlational analysis, which examines those variables printing in the same log instance with the user variable. On the other hand, the system-related variables are discovered by analyzing instance fields checked as exception or error conditions. These variables are regarded as critical state variables since their values indicate abnormal error conditions. This approach is implemented in a tool called MPC Checker, which author claimed helped developers to fix 20 reported bugs and confirm 23 bugs. All of them were critical. One of the bugs was dangerous that the developers didn't want to disclose, and overall the software had around 13.7% of false positive rate. Now, these are some contributions done by authors. Authors mentioned that they did studies on real-time distributed systems with MPC vulnerabilities and found that among the total of 152 vulnerabilities done on those 10 systems that are given in table 1, 95 of them were MPC vulnerabilities. They also found that MPC vulnerabilities, insecure interfaces, and insecure APIs make up to around 42% of all cloud security vulnerabilities. They proposed a log-based analysis to detect the MPC vulnerabilities in the distributed system, and they developed MPC Checker, a vulnerability detection tool which successfully reported 44 new critical bugs in 6 real-world distributed systems. In the table, the first column shows the systems on which the studies were done. The second is the type of the different services that are provided by the systems. The third are the checking mechanisms that the authors used on each of the systems. We'll be getting more in detail in next few slides. And the last column shows the number of bugs that were found in each of the system. Moving forward, let's look at how the vulnerabilities were collected. As we know, there were a total of 95 MPC vulnerabilities from total of 152. So 49 vulnerabilities were collected from the CVE database. 368 CVEs of the 10 system mentioned before were examined, and 49 access control vulnerabilities were filtered out. The remaining 103 vulnerabilities were extracted by querying each issue tracking system with these filters like access control, authorization, security check, etc. There was only one system that didn't suffer from any MPC vulnerability, that was Kafka, because it authorized external requests with API hooks, effectively preventing flaws in the system. Now, there were 3 findings that the authors understood by studying all the systems, and they are as shown below. The first finding is permission checking mechanism. The system under study implement different mechanisms for permission checking, with each system adopting one or more mechanisms. All permission checking APIs in the studied system implement checks by testing user variables in the conditional statements. So let's talk about all 4 of them. M1, permission checks are conducted on the same node, that is, the user will send a request and the server will invoke permission checking API to check the user's privilege. M2, permission checks are done on another node. This means that rather than the server node invoking the method itself, it will send the request to an authorization node using a mode of communication. It will then receive a response and act accordingly. M3 mechanism is known as a token-based authorization. In this case, the user will communicate with an authorization node directly and ask for a token representing the user's permissions. The node will return this token, and whenever the user wants to access anything on the system, they will send that token to the server to check for authentication. M4, the user does not communicate with the server directly, but rather than the authorization node, it will handle authorization and then communicate with the server to get a response. Okay, talking about an example, author states that permission checks are done ad hocly by testing user variables in conditional statements instead of calling wrapped APIs. Around 31 of all the MPC vulnerabilities found by authors were fixed by ad hoc permission checks. Ad hoc permission checks play a crucial role in mitigating MPC vulnerabilities by ensuring that only authorized users can perform privileged operation. Figure 3 in the paper presents an example of an ad hoc permission check, yarn 8455, that fixes a vulnerability by directly testing the accessing user. That's given in the lines 3 to 5. So the second finding that was found out by the authors was privileged operations. Among the studied MPC vulnerabilities, a significantly major, that is 84 out of 95, involved privileged operation accessing user-owned data without proper permission checks. Around 50 out of those 84 were not created by the users. User-owned data can be directly created by the user, or it can be transitively derived from other user-owned data. The remaining 11 modify critical system related variables, where 10 of them are used as error conditions. Distributed systems often divide large data chunks, that are data created by the user, into small pieces. Those small data pieces are managed by the system and typically invisible to regular users. That is, they can only be accessed by the administrator for system maintenance. As an example, in the figure below in HBase, a table object is created by a regular user and can be divided into small regions, object of type region. Both table and region are user-related types, which are managed by the regular user and system user respectively. Accesses to variables of both types, that is region and table, need to be checked. Moving forward, in figure 5, in the paper, it illustrates an example scenario highlighting the vulnerability related to a critical system state modification without proper permission checks in a distributed system. The vulnerability scenario method involves the method shutdown data node, which is an RPC method response for shutting down the node in the distributed system. The critical system state being manipulated is denoted by the instance field shutdown in progress, which indicates whether the node is currently in the process of shutting down. This process vulnerability scenario, the shutdown data node method, falls to include a permission check to verify the accessing user's privileges before initiating a shutdown process. The submission of a permission check exposes security vulnerability where any user, regardless of the authorization level, can trigger the shutdown operation. Okay, the finding 3 is component interaction. 28 out of 95 vulnerabilities detected involved intercomponent operations and communication. This means either the privileged operation or its fixing permission checks were performed remotely on another component. So in this example, a API closed region wraps the request as a closed meta handler event in line 6 and submits it at line 7. The event is then dispatched to its corresponding handler, that is close region handler.process, with the privileged operation at line 12 is invoked to remove regions from the system. Hence, the event sending call at line 7 is eventually handled by its corresponding event handler. To preserve such semantics, we need to link event sending call to its corresponding handler. Let's talk about the tool that was created by the authors to check for these MPC vulnerabilities, which is called MPC Checker. So MPC Checker tool consists of 3 main steps. First is to automatically info user and system related variables by analyzing runtime logs, identifying permission checks and privilege operation from the info variable, and the last one being privileged operations which are not guarded by permission checks are reported as MPC vulnerability. So we'll be going each step in detail in the next few slides. MPC checker also requires manual specification of username, public interfaces, and intercomponent communication patterns. So let's talk about user and system related variables. Inferring user-related variables is done through log analysis. The authors delve into the process of identifying user-related variables in distributed system. It's a crucial step in detecting MPC vulnerabilities. Identification of user-related variables is essential for understanding and safeguarding privileged operations that involve user-owned data. So how do they do it? They construct regular expression patterns for logging statements, abstracting logged variables as dot star while keeping string literals intact. By matching these patterns with runtime logs, they extract concrete values of logged variables. So there are 2 rules that are thought of when applying analyzing logs. Rule 1 is a variable is user related if it is accompanied in a log instance with another user variable or user related variable. In figure 9, the extracted log pattern for each statement is highlighted in comments. Variables printed in the logs are abstracted as dot star in the log pattern, and their runtime values can be obtained from the matching log instance. For instance, the log pattern creates the same table and matches with the log instance user1 created table 1. As a result, the runtime value of the logged variable users and table are extracted as user1 and table 1 respectively. So in the example of figure 10, variable, table, and user appear in the same log instance, hence table is a user related variable. Note that the variable table have multiple runtime values, that is table 1 and table 2, suggesting that a user can create multiple tables at runtime. Looking at rule 2, Rule 2, a variable is a user-related variable if its type matches with the type of the user-related variable. So there are three things to consider when we do that. The first one is the inheritance relationship, which means that TA is an object type identical to or inherits from TB, TA and TB being types, two different types. Second is collection types. If it is a that means that the collection of one element type matches with another type TB. And the third is indexing fields to identify variable related or user owned data. That means if it has an indexing field whose type matches with the other type, that is TB. Moving on to system related variables. System related variables can be discovered based on the observation that they are often tested as error conditions, and the types of conditions to consider are that statements throw exceptions and return statements following faulty level logging statements as given in the figure. System states are commonly stored in instance field within the program. By identifying conditional statements that check these instance field, the tool can recognize variables representing critical system states. The second step in MPC checker is to identify permission checks and privileged operations. So in finding one permission, if you remember finding one, permission checks are implemented by either directly testing user variables or calling APIs that wrap these tests. Permission checks are implemented through conditional statements, hence all conditional statement testing user variables are permission checks. And if an API has a permission check post dominating its entry, then it's a permission checking API. Sometimes an API performs permission checks only if the authorization service is enabled as shown in the code snippet below. When security configuration is not enabled, the authorization object PC is null and the check is at line 4. That's at line 4 is skipped. Without considering this case, we will report, the authors have reported many MPC vulnerabilities which can be triggered only if the security configuration is disabled. Privileged operations within the distributing systems that involve accessing or modifying critical system states or user-owned data can have potential impact on security. So the authors considered the read and write operations as privileged operations, and they are usually invoking APIs to modify collections in the system, that is insert or remove function, that's the write function. And privileged user related variables are identified when when a function returns sensitive user data. So that is the read operation. Detecting MPC vulnerabilities. Okay, MPC vulnerability is created when there exists a path from the entry of the program to a privileged operation. A request is regarded as a privileged operation if there are unguarded privileged operations in its corresponding handler. Otherwise, it is a permission check if there exists a permission check which post dominates the entry of the handler. IFTS approach. IFTS means interprocedural finite distribute subset. It checks if the privileged operation is guarded by the permission check or not, and if it is not guarded, then it's an MPC vulnerability. Second is intercomponent. In detecting MPC vulnerabilities, we have to take care of intercomponent communication. Analyzing distributed systems as a whole can be challenging due to large combined program size of all the components. So instead of doing that, we can handle intercomponent communication by proposing a user-specific approach to resolve the target of client request. By treating requests as direct calls to their handlers, different components of the system can be connected and analyzed in a standard manner. Also, instead of linking all components together for analysis, the authors apply function summarization to determine whether a request is handled by a permission checking API or a privileged operation. The second thing is data flow analysis. As previously mentioned, IFTS algorithm solves a good number of interprocedural data problems. It operates on a so-called exploded graph. At each point of the interprocedural call graph, a node is introduced for each data flow fact. Edges of the graph represent the data flow throughout the function between the nodes. A program is realized when there is a clear path from the program entry to the intended node. For the MPC vulnerability detection, the data flow value is either true or false, denoting whether a point is unguarded or not. That is, whether there exists a path from the program entry to the point without checking permissions or not. Equations 1 to 3 give the data flow functions. The analysis propagate data flow values forwardly along the ICFG of the program. Let's take an example to understand how the MPC checker works. The checker initializes the data flow fact as true, as mentioned at node 1. It moves on to node 2 and sees that another function is being called, which is unassigned. And node 5, this function is determined to be privileged and unguarded. So the fact is set and kept at true for this data flow, and the data flow is 1, 2, 5. As for the other data flow going through 3 and 4, the fact is set to false, and the vulnerability is successfully reported when the fact at line 19 is true after merging facts along different paths. Let's talk about the limitations of MPC checker. There are three main limitations that the authors have proposed in the paper. The first one is manual efforts. One of the concern is the manual efforts involved in specifying public interfaces and communication patterns. Table 2 presents the number of specifications of the 6 Java systems they evaluated, the authors evaluated. Column 1 gives the number of specified public interfaces, which is at most 3. HDFS, public APIs implementing those interface methods are automatically derived and their numbers are much larger. That's given in column 3. Compared to interfaces, it takes more effort to specify communication patterns. They manually provide 188 communication pattern for YARN and 145 for Cloud Stack. Column 7, that's given in column 7. Yarn dispatches events and WebSockets to different handlers at distinct context. As a result, an event or a socket client is often cloned multiple times, each with a distinct context. Okay, moving on to the permission checks. They have only considered the simple permission checking implementation where a user is conditionally tested. This trade-off works well for the 10 distributed systems under study. However, it may not be generalized to the other implementation. For example, token-based authorization with permission checked against a token. Look, moving on to the third one, privileged operations. They have introduced a novel log-based analysis to automatically identify privileged operation from the inferred user and system-related variables based on the assumption that accesses to these variables are privileged. So one can argue that this assumption is not true. System-related variables may be harmlessly modified and user-related variables can be exposed to public without disclosing confidential information. So there's no simple yes and no answer to the argument. However, in their experiment, only 5 false positives were caused by incorrect privileged operations, suggesting that there's some truthfulness in their assumption. Okay, moving on to the next one, evaluations. Okay, they have evaluated MPC checker using 6 distributed systems within the Java, that is HDFS, HBase, MapReduce, Yarn, etc. For each system under the evaluation, they've pulled its latest trunk version to evaluate the capability of MPC checker in detecting the new MPC vulnerabilities. They've tried their best to compare with previous approaches by manually verifying whether a reported bug can be detected with previous consistency checking mechanisms or not. So evaluation answers the following research question. The first one is, how precise does MPC checker identify privileged operation? What is the effectiveness at detecting these bugs and how efficient it is? Let's talk about precision. So whether the authors precisely identify the privileged operation or not. Column 2 to 4 in table 3 are the number of related variables, 5 to 7 the number of privileged operation, and column 8 the number of checking APIs as for each system. MPC checker automatically infers thousands of user related and system related variables that are given in column 2 and column 3 respectively. Accesses to those variables generate hundreds of privileged operations as shown in column 7. An immediate question arises, are these operations really privileged? The authors have manually checked these operations and confirmed that all of them do access user or system related variables as expected. Later experiments further confirmed that most of the accesses were really privileged, real privileged operations. Only there were 5 false positives. Moving on to effectiveness. There were two ways of checking effectiveness. The first one is identifying existing vulnerabilities, and the second one is detecting new vulnerabilities. So, moving on to existing vulnerabilities, 4 vulnerabilities were not detected due to the reflection. When MPC checker fails to find the privileged operation in reflective method calls. Other than that, MPC checker was able to detect 57 existing vulnerabilities with 7 false negatives at a recall rate of 87.8%. These vulnerabilities access 49 different variables, 25 user resource types, and 54 different operations. Okay, new vulnerabilities. This table gives around 44 new vulnerabilities that were reported by MPC Checker. For each reported vulnerability, they have listed a public API that exposes the bug, type of privileged operation, that's in column 3, related variables in column 4 to 6, and the number of involved components given in column 7. Except for Zookeeper, MPC Checker detects MPC vulnerabilities in all systems under evaluation. HDFS has by far the most number of vulnerabilities, which is around 24, followed by HBase and then CloudStack. Most detected vulnerabilities, that is 36, are caused by unprotected privileged write operations, and the rest 8 vulnerabilities leak user-owned data. That's given in column 3. Column 5 lists the related variable for each vulnerability. 16 out of 28 related vulnerabilities are primitive objective type. That's given in column 4, and 27 out of 17 variables are user related, system related. 27 and 17 variables are user related and system related, respectively. As shown in column 7, 20 bugs involve at least 2 components, and HDFS 157521 is triggered by 3 components together. They have patched all the 44 reported vulnerabilities. Among the 44 bugs, 20 of the patches have been accepted, and another 23 bugs have been confirmed by the original developers. The bug MapReduce 733043 is still under review. All confirmed bugs are labeled as critical bugs and can be easily exploited. Moving on to efficiency. The efficiency evaluation is presented in table 6, which reports the time taken to analyze each system. Column 1 presents the number of lines of code for each system, and column 2 gives the number of log instances generated by running the built-in workload of each system. The number of log instances are small except for MapReduce, and all other systems have less than 1,000 log instances. Column 3 to 5 shows the breakdown times of each step, and the total analysis times are given in column 6. The majority of analysis times are consumed by the IFTS solver in step 3. The analysis time is directly related to the number of public APIs of each system, since they run the time-consuming IFTS solver once for each API. So it takes the longest to analyze CloudStack, which is around 17.5 hours, 17.15 hours with around 1,764 APIs. Zookeeper can be analyzed in 3 minutes because it has only 7 public APIs. There were 2 case studies done by the authors. Okay, the case studies focus on 2 new bugs reported by MPC Checker. Let's talk about the first one, which is HDFS 157521. It was identified by the Web API Interface FSCK, where a user-related variable block info was leaked, potentially exposing confidential information such as file names and location to unauthorized users. This is given in figure 13. API returns all block information, including information for blocks belonging to other users, to the requested sender, which includes block ID and its containing file. However, the file name and location may be confidential to the requesting user. This vulnerability could allow an attacker to access secret file names in a confidential directly by invoking the API FSCK, bypassing the file system access control mechanisms. Moving on to the second case study, which is HBase 2544132, given in figure 14. This bug is reported because a user-related variable called state is returned from the public API leaking sensitive info. The checker also detects that one of the functions, evict block by H file name, is an expensive operation. So if the attacker executes this function multiple times, it may cause denial of service. This is all about the paper. We have come to conclusion. In conclusion, MPC checker program is a robust, you can say robust tool to check for MPC vulnerability in the distributed systems. It utilizes log-based analysis and info user-related and system-related variables to check for privileged operation. The authors evaluated the tool with 6 widely used distributed systems and found that it detects vulnerabilities at high precision with a recall rate of 87.8% and a false positive of 13.7%. Among all the 44 MPC bugs, 31 of them would not be detected by existing techniques. Only one false negative was observed due to a missed privileged operation, and only 5 false positives are caused by incorrect privileged operation, indicating the preciseness of the program. Thank you.